This is the first of two videos about dominance matrices and modeling with dominance matrices. So an introduction here. So we use dominance matrices a lot when we have to rank things. So they have to be put in an order, which one has the best performance or the biggest influence, things like that. So ranking is a very prominent application for dominance matrices, hence the name. So, for example, a tournament, whether it's a sport or some sort of gaming tournament. So, tournament is a common application, common context. So, in this tournament or this competition, not all players meet. Okay, sometimes in tournaments it is possible that not all participants or players meet, and similarly players might not meet or play each other the same number of times as with other players. So they may not play each other as many times as with other combinations of players. Equal number of times. Okay. So here's a very simple example. We've got 4 players: Alan, Brian, Carlo, Dennis, represented by the letters A through to D. They've had this performance or these performances before. A defeats D, D defeats B, C defeats A and C defeat B and D. Defeat C at the end. So we absorb that first. So this information can be represented, if we like, as a graph or a digraph, which is like a network diagram. So we could, different ways of doing it too. You can give it more of a 3D tetrahedron type look, or you can just give it a 2D sort of look. But one way of doing that is set it up. I'm just going to go around sort of clockwise-ish, set up my little digraph, and basically, because these people all play each other, we can make connections between each. So we've got from A to B there, straight line, B to C, straight line, C to D, straight line, D to A, straight line. But there's more than that, so we can connect D and B together. And lastly, I needed to put C connecting with A. So now what we do, we use a little convention where we put arrows on the digraph. The direction relates to who defeats who. So the first bit of information, A defeats D, so we fire our little arrow towards the D. D defeats B in the next bit of information, so likewise arrow heading towards the B. Then C defeats A, C defeats A, and A and C both defeat B, so they both have arrows pointing towards B, player B. The last one then is D defeats C, and that's drawn sort of a tetrahedron shape on mine. So I didn't draw very straight arcs on mine, so but it does the job. Another common way of showing this information is with a matrix M, which shows you don't have to write these little letters in these labels, because in a matrix we generally don't label rows and columns, but just for the sake of instruction. So if you go along row 1, it's the story of what happens to player A. Now player A can't meet himself, so there'll be a 0 there. A defeated B, so a 1 is written there, and then A was defeated by C, so a 0 pops up there. A defeats D, so we have another 1 there. Now the total of that row is 2. I'll talk about that a bit more in a moment. So we have now B, the story of B. We do it the same way, and by the way, by the time we get to here, we'll get a 0 there on that diagonal. In fact, the whole leading diagonal, because a player can't play itself, so they're going to be 0 straight away. I'll quickly now fill out the rest, and we get this. So we can see that we've got, if we add the totals for each row, we get 2, 0, 2, 2. So that gives us a sort of a crude rank. We know that A, C, and D have played and have been more successful than player B. In fact, player B has achieved the total score of 0. But it hasn't done much in terms of ranking it, because all we know is that B is the worst, and A, C, and D seem to be the same based on this data. And so we're going to talk about that issue and what we can do about it and how we can go further on. By the way, a refinement to this model too, if draws are possible, each player in the draw gets a half is one way of getting around that. Alright, so a win equals 1 over another player, a loss for a player gives a 0, and a draw, if required, each player gets a half. There'll be no draws in this particular situation that I'm dealing with right now. Now the numerals in orange there, we can consider that as a vector or a column matrix, column vector, column matrix, and we can call these ranking vectors. Sometimes they're called dominance vectors as well. It's often given the symbol R, and that's a pretty crude one right there, so we're going to develop the model further. So what we're going to employ is the transitive nature of the situation, which I'll run through in a minute. And we're going to get that matrix M and multiply it by itself. So M times M gives M squared, as you can see there. And that's M squared, the result there. It's a different matrix. So the transitive nature makes a big assumption here that the initial conditions in the task are always true. We take them to be true or so. So going back to the question, so this based on past performances status, that condition holds for the whole model. We know in the real world that's not necessarily the case. There's lots of factors in the real world, but for the sake of this model, we base it on those past performances and we stick to it in this given model. So in general, in maths, if we have some value or variable x is less than y, and if y is less than z, then we can conclude that x is less than z. That's called transitive nature. So in this example, that would be if we see that A defeats, from the question, A defeats D. We can see that there. That one. Okay, and these all come from the original question. So if we go back to the question, A defeats D, and we've got the, sorry, I couldn't remember, D defeats C. And we have, that means A can defeat C in the M squared Now let me explain the m squared a bit more. But just before I do that, it really relates to that mathematical idea above. Now we saw that in fact C defeated A in terms of direct matching, but to separate those two, we know that A can beat somebody who can beat C, so that adds to A's performance. So while directly C will clobber A, but indirectly A can beat somebody who can beat C. So that has to also be taken into account if we want to rank them. So both of these things are in the mix, and this will help us separate players and get around that initial problem. In terms of the digraph, what m squared does, it looks at the total of the values when we look at two steps to get from two path steps to get from one point to another. So I just traced from A to B using a 2-segment or 2-branch step, and there's other ways of going from A to B. There's that one, and there's also this one. Sorry, that last one is incorrect. There's only 2 paths. So what we do is m squared basically does that. It looks at all the 2-step dominance points, and it adds them together, and the sum total at the end will be our 2-step dominance vector, our second stage. So what we got here is another result, which I've just added there, and basically we seem to have some improvement in working out who's who. We have a leader, we have person in last place, and then we have C and D at the bottom there, which are in the middle somewhere. This is not perfect, so we can try and extend on the idea by going for m cubed, which is just taking the idea a step further. It's how many 3-step paths and the points associated with them. Now on this particular network, we're not going to go beyond m cubed, because that is the largest number of steps to go between any 2 points without retracing over. So if we want to go from A to B, and we want to look at 3 path points, 1, 2, 3. Okay, we can do it that way. You can't do a 4-path point on this, because if you go that way, that way, that way, you've gone back and touched A again. Okay, so that won't be valid. So this one will go up to m cubed, but in some bigger models you can go further than that. It's about making choices and refining the model and checking the effect of it and evaluating that. The value we get at the end, 2012, is perhaps a slight backward step on what we got just there, 302 to 2012. It's it's worth considering. So what we do is to get our ranking, we usually in general do what you see there, the ranking matrix or the dominance matrix. By the way, the M's are sometimes denoted with a D in some sources too. That you might see that as a D. It's just a symbol anyway, but it's the original one from direct contact. So we saw C beat A before, and yet with the secondary we saw it switch around and A had more dominance. Now you have to decide what weightings to put on them. Typically these values there are less than 1. You can see what this example here, the overall ranking is that's a pretty typical one. Okay, and we couldn't go past cubed in it. So it all depends on the model.